So officially starting the recording. Happy Garbage Day, folks. Welcome back to school. Can you believe that we almost missed Garbage Day this morning? Seriously, I was pulling out of the driveway and the garbage truck was coming down the street, and then I noticed at the last second that our garbage was not out on the curb. So I was the person who jumped out of the car, ran into the garage, got the cans out just in time. I'm like, sorry. It's like, how off-brand would it be for me to miss Garbage Day of all things? So we got it just in time. So happy Garbage Day to everyone. Thank you for submitting your project outlines. I have downloaded them and started processing them. I am making a spreadsheet as to who can present when and who is working with whom. And my plan is to get that part figured out so that you can plan on when you'll be presenting. And then I will provide you with feedback on your plan in order of people who are going first get my feedback first, and people who are going last get it last. So my goal is to get you information back as soon as I possibly can so that you can start working on these things, as well as I will develop a more detailed rubric, a set of expectations, that kind of thing. So, but it is just a presentation, it's not a paper. I want the heavy lifting to be on and actually running the analyses and trying to understand them, and once you get to the point where you have something worth writing about, then hopefully you can write the paper over the summer on your own terms, and I'm happy to be involved with that or not, as you wish. So that's the plan for those. Let's see, your next homework isn't for a couple weeks. It will be due, I think, maybe 2 weeks after spring break, so that's not a thing you need to worry about yet. It will be on this stuff. It will be another CAN data type of exercise. So my goal for this week is to get far enough along to where you would be able to do a homework on this topic. And otherwise, I think that's all my announcements, scheduling stuff. Anything I'm forgetting? No, don't think so? Okay, good. I don't think so either, but I'm known to forget things sometimes. So we were talking last time, heading into a new unit about how to model time-varying predictors. So I will tell you folks, in terms of your projects, like if you have time-invariant predictors you want to include, background variables like baseline variables, you can have as many of those as you want, because there's only so many things that those variables can do, and including them is not adding a lot of complexity. The same is not true for anything that varies over time, whether you're thinking of it as a predictor or an outcome. Every variable that varies over time could potentially need its own growth curve model to partition the variability into intercepts and slopes and residuals. I'm going to talk about sort of in the context of fluctuation first, how to model time-varying predictors, because then we don't have the time slope component of it, but then adding that part after break would be the continuation of this saga. So we talked about the idea of each time-varying predictor last time being 2 variables instead of 1. Some people are going to be higher than lower than other people on average. That, for all intents and purposes, is like the time invariant level 2 part of that predictor. The extent to which people have higher averages on a predictor than other people, more than other people is the key word. But because you've measured it over time, then some occasions are going to have higher values than others. And that's the level 1 within person part. So the language that I'm going to use here, I'm going to try to be consistent. It's like there's a part of the variable that's level 1, and there's a part of the variable that's level 2 in terms of the information that it contains. And that's what's confusing, is because on the surface of it, you might look at, say, a level 1 predictor like this and think, well, I'm going to put it in the level 1 model because it's a level 1 predictor in the end. But you can't do this, because the problem is that the one fixed slope that this level 1 predictor is getting has to describe both the effect of being a higher person than other people and having a higher occasion than other occasions at the same time. So this problem, the idea that we haven't differentiated between person relationships from within person relationships, I call this a smushed effect. I would also accept an alternate spelling, by the way, of OO for smooshed. If you prefer that way, that's fine. If you feel silly writing smushed in a paper, then you can use any of these other words. My favorite probably alternative is conflated, because I feel like that conveys the same sort of idea. Composite is ambiguous. There's a lot of ways in which that word can be interpreted, but those are some synonyms that I've seen. So our task is to find a way to allow this longitudinal time-varying level 1 predictor to have the level 2 part of it have its say in the model, and the level 1 part have its say in the model at the same time. That's what we have to do. And that shouldn't sound like a new idea, because we have literally done that already with the outcome. What I call random intercept, we could also say is the level 2 part of y. Random intercept is person mean differences, right? Some people are higher than other people on the outcome. That's level 2 variability, the level 2 part of y. Likewise, E, why are you off your line today? Why are you off your person mean in this case? That's the level 1 part. So we have to find a way to pull apart this level 1 predictor analogously to how we let the model pull apart the level 1 outcome. If we're doing this within univariate MLM software, we have to do the pulling apart ourselves using observed variables. The alternative, if we can use multivariate software, is to let the model pull apart X in the same way that it pulled apart Y. Okay, I feel like I'm like talking fast again. With me so far? Okay, so this is big picture forest stuff, right? The trees are forthcoming. But if you can hang on to the big picture, then you can immediately recognize alternative situations in which this problem is not being addressed, such as skipping ahead many, many slides to show a picture. Here's a picture on slide 42 from the M+ manual describing a structural equation model for y, where we have an intercept and a slope and a time-varying predictor that they labeled A. And in this model, these paths from the time-varying predictor to the time-varying outcome are smushed, because there's nothing in here that splits the A variable into its between part and its within part. And if you're thinking, well, quit picking on M+, okay, I'll pick on Lavon. They have the same picture in their manual. They just changed the labels. They're using C instead of A. So this problem is very, very common in SEM in particular, because it's not obvious from a single level model how you would split the two parts. It turns out that the solution is, well, why can't I just give an intercept to this other variable just like I have this one? And that's exactly what we would end up doing. So eventually headed to the idea that we have an intercept for the predictor as well as an intercept and potentially a slope for the outcomes. So that's the long shot. By the time we get there, that part will be obvious. But for folks who have only had SEM and who have never had multi-level, these things are not ideas that they may have seen. The centering, as it is known, is a multi-level modeling convention, not so much an SEM convention. So diagrams, let me pick up here on slide 6. This is my way of trying to convey what a smushed effect is, where I have, you see the green and the purple, the levels? Yeah, I should get extra credit for this gradient thing. I really like this. But throughout the lecture, I'm using colors in a very deliberate way to keep track of different ideas. So the green is going to be the level 2 between person mean differences. Purple is going to be level 1 within person residual. And for Y, we let the model carve up the level 2 and level 1 parts into these variance components or piles. For X, we haven't done that. So if we allow a slope of X, it's essentially having to do both the level 2 part and the level 1 part at the same time. Only in the situation in which those regression coefficients are exactly the same is this smushing or conflating acceptable, and that's not going to happen. The reason it's not going to happen, there we go, wanted this piece right here, is because these are unstandardized regression coefficients. If we think about effect size in terms of a standard deviation of X versus Y, in this context, go back to the picture, standard deviation at level 2 is going to be necessarily different than standard deviation at level 1 unless your ICC is exactly 0.5. So everything would have to be perfectly balanced for you to even have a chance of these coefficients being on the same scale, like perfectly, not balanced, equal, equidistributed, that's the word I want, equal split. Plus they mean different things. Like if you think about what are the forces that might create more chronic stress in someone's life, and what would separate somebody who has more chronic stress from a different person who has less. That's a different set of circumstances, causes, and effects relative to why is it that on certain days I feel more stressed than I usually do. That's a different set of causes and effects. So conceptually, it makes sense to me that these would not be the same coefficient, the same relationship, because they mean different things. Longitudinal data allows you the opportunity and the responsibility to do both at the same time. With great power comes great responsibility. Isn't that a quote? Is that Star Wars?
Spider-Man.
Spider-Man. Okay,
Yeah.
yeah, I don't know these things.
That was close enough.
Close enough? Thank you. Yeah, I used that line at the end of an article that I wrote last year, and I was like, I hope no one asks me where this is from. I know what it is, but great power and great responsibility. That's the key here. Okay, questions so far? So then if we translate the idea of slopes out of parts of variables, there are 3 different kinds of slopes that we can observe for any time-varying predictor at a minimum. So as long as this time-varying predictor has variability at both levels, meaning that it has an intraclass correlation between 0 and 1, so if it were 1, it would be a time-invariant level 2 predictor. If its intraclass correlation were 0, it would be only level 1 within person. Most of the time, it's going to be some blend of both. So this is built on a precursor that it has both levels of variation, therefore can have relationships with an outcome at both levels at the same time. Number 1, is there a within-person slope? So level 1 within person goes together. That's the idea of relative to your own self as a baseline. More than usual or more than baseline. I'm going to stick with usual for this lecture since we're talking about the fluctuation type of context. So if I have a higher X predictor than usual at a given occasion, does that translate into a different outcome than usual relative to my usual levels is the key. And it can be at the same time or it can be at a later time. So that they're equally within persons. I don't care which you pick. You can think of this as concurrent or lagged relationships. Either one of those works. If there is a within-person slope that's non-zero, then that within-person part of the time-varying predictor will reduce the level 1 residual variation of the outcome. So the level 1 part of the predictor explains the level 1 part of the outcome. In the same way that level 1 time explained the residual variance at level 1. It's just that time last semester only had level 1 in it. Level 2 then, same exact idea, but a different point of comparison. So level 2 between person slope, if I tend to have a higher X than other people, if I am higher on average on my predictor, am I also different on average from other people on my outcome? So more than other people is level 2, more than usual is level 1. If so, then the level 2 part of the time-varying predictor will explain the level 2 part of the time-varying outcome. Random intercept variance. Okay, with me so far? Cool. Now the third one. This is tricky. There are 2 ways to interpret what is known as a contextual slope. One of them to me will make more sense to first. A contextual slope is the between slope minus the within. It is the direct test of whether those 2 relationships are the same, whether smushing them together would be okay. That's the easier way to understand it, I think, what a contextual slope is. The harder way is that it represents the incremental contribution of a person's mean after controlling for their current value. That is weird in longitudinal data. It makes a lot more sense in cluster data. So we're going to sort of sidestep this last one for the time being and just focus on the first 2. and then we'll come back to it. Because these ones are easy, more than usual or more than other people. So here are the three choices then. How do I take this level 1 predictor and introduce two different slopes for its two parts? Option number 1, within a univariate multi-level modeling framework, so Elmer, mixed, etc., what is known probably almost universally as person mean centering. In clustered data, this goes by group mean centering, cluster mean centering, centering within context, centering within clusters. It has like 8,000 synonyms. But in this approach, which I will show you first because this is my favorite, this is like do this, do not do anything else if you're going to stick within this univariate framework. We are literally carving up the predictor into its two parts, and then we put the two parts in a model. So I refer to this more generally, this type of strategy, as variable centering, because we're not centering with a constant, we are subtracting off a variable. It's a different kind of centering, because what variable you pick is going to change what the slope therefore means. So we're going to take the original time varying predictor, subtract off the person mean. The person mean is going to go into the model at level 2. The new within person part is going to go into the model at level 1. The benefit of doing it this way is that you always know what you get back. You cannot screw this up. You're doing the heavy lifting on the front end and setting up the variables, and then the back end is straightforward. It will always yield either a level 1 within slope for the level 1 part of the variable, or a level 2 between, the end. And if you leave out either one, you're assuming the thing you left out is 0, the same as any other model in the history of the world. Any slopes that are not in your model are thought to be 0. Option 2. What is known as grand mean centering, I would say most commonly, I call this constant centering because it doesn't matter if you subtract off the grand mean or 6 or leave it uncentered at 0. What constant you pick is irrelevant. This approach does not carve up the variable into its parts. It leaves the level 1 variable having both parts put together, and it solves the problem of smushing through a statistical partialing process behind the scenes once you put in the person mean. This option is probably much more common, particularly for cluster data instead of longitudinal, but it is really easy to screw this up. This will yield level 1 within slopes once you've entered the level 2 part of the variable, but then you get level 2 contextual instead. Third.
Wait a second.
Yep, go for it.
So what are we exactly putting in the model here?
You are putting in basically the original level 1 variable,
Yep.
centered at a
Mine's
constant,
Yep.
and the person mean. But they're redundant because the level 2 part is still inside the level 1. So you're adding in level 2 twice.
Got it. Okay.
Is what happens. And so then it's like, once they're together, because they correlate, each has a unique effect after controlling for the other, and that unique effect is going to be different if the other predictor is not included.
Yep.
So what they mean depends on whether the other one is there, and it can be either wrong or incomplete or correct, depending on your configuration. So this is just like the outline slide of all the,
Yep.
like, we're going to go into each one of these and see what happens. But these are like your three main choices for how to handle this. So these are the two that require you to make observed predictors out of a time-varying predictor because you're working within a univariate framework in which only Y can have variance components. The third option is multivariate. Within single-level or multi-level SEM, you can do it either way. This goes by a bunch of names too, but the one I think that is most... I'll say it matches the best to me is latent centering. Because you're just saying, okay, well, I'm just going to treat X like Y. It gets a random intercept, it gets a residual, they're latent variables instead of observed boxes. Then I can have paths going, at each level of the model like I'm used to. So that's a great idea. Except what you get back is very, very difficult to tell whether it's between or contextual. And I got so mad about this once I finally figured it out that I had to write a whole paper about it. So we will go into this one as well. And this problem of between versus contextual holds whether you have slopes for time in the model or not. So it's not just fluctuation that this happens. All right, ready for option 1? Cool. Person mean centering, here we go. So in person mean centering, or PMC, as I'm going to abbreviate it, we take our time varying x, so in the notation it's xti. We carve it up into 2 variables that represent its level 2 part and its level 1 part. So at level 2, I compute the person mean, so x with the bar over it, sub I. I center that person mean x at a constant so that 0 means something, so that I keep a reasonable interpretation of my fixed intercept. Doesn't matter what constant it is. So I've labeled this C2, meaning the constant at the second level for the centering. Doesn't matter. But let's say that I use the grand mean, so the mean of the person means. If I did that, then a positive value of person mean x would mean that I have more of x than other people. A negative value would mean I have less of x than other people. And 0 would mean that I'm at average. So this person mean predictor is a time invariant level 2 predictor. It's treated the same as if it were a baseline characteristic or a demographic characteristic or anything else that doesn't change. It is a level 2 predictor. At level 1 then, this is variable centering. I'm going to create a variable I'm going to call within person x, ti, it varies over time, out of the original time varying x minus the person mean. And note it's the uncentered version here. Otherwise it would be doubly centered, and we don't need that. So under this centering scheme, I have taken away all of the variability that was introduced by these person mean differences. So a 0 value of within person x means I'm at my own mean, like on an average day or an average occasion. A positive value would mean that I have more today than usual. A negative value would mean I have less than usual. So if I put these 2 predictors in a model, my reference point for the intercept would be, this is the expected outcome for an average person on an average occasion. The reason that I like this is because it makes all the interpretations simplified. This is only level 2 variation, therefore the only kind of slope it can have is a between person slope. The purple is only level 1 variation, therefore the only kind of slope it can have is a within person slope. That's it. Okay, with me so far? Okay, picture time? No, equation time, then picture time. So this is what it would look like if I had a fluctuation model, so starting with just an empty model for y and adding in the time varying predictors just so we can kind of isolate that part. If you already had figured out that y needed, say, a random linear time model, that would already be in here. So we're just talking about the addition of the time varying predictors part. So within person xti would go in at level 1. It only has within person variation to it. Person mean x, which is centered at a constant so that 0 is a good value, would only have level 2. So that means that the coefficient that goes with the within person x is directly the change in y for a 1 unit change in x where it's a unit more than usual. The key here is change relative to what? More than usual, 1 unit more than usual is what the gamma 1,0 slope is going to capture. The other one then is the level 2 between person slope, 1 more unit than other people on average. So there's still slopes in that this is the change in y for a 1 unit change, but change relative to what? Relative to a person mean is level 2. So this is people who have a higher mean than another person. At level 1, it's within myself relative to my own mean. If I'm higher today, does y go up today? Or the next occasion. This is a contemporaneous model where we would expect that the level 1 effect is at the same time unless you somehow lag the data. I have an example of that actually built into the slide deck. So what makes this work is that within person x and person mean x are uncorrelated. They each do their job at their own level. They stay in their lanes. Just picture like a highway where everybody's just flowing, through traffic and everybody stays in the lanes. No one's trying to merge, none of that craziness. So it's very straightforward to interpret their effects. If you leave either of them out, you're just assuming that that slope is 0. Here's what it would look like graphically. So we've taken what used to be x, carved it up into its level 2 part, person mean x, and its level 1 part within person x, and we've given them each a distinct slope. So person mean x should be able to explain the random intercept variance of my outcome. Level 1 within person x should be able to explain the level 1 residual variance of my outcome. Here's some pictures. So in these pictures, I have severity as an outcome, where worse is higher. I have time-varying stress as a predictor. Time is not in the picture, because after we fit the right model for time, we don't need to worry about which occasion it is. What we need to worry about is how stressed you are at this particular occasion and how severe your outcome is at this particular occasion. This picture shows the time-varying stress, the original values on the x-axis, and then it shows predictions for 3 different kinds of people. Mean stress of 6, mean stress of 5, and mean stress of 3. So let's you can think of these as high stress, medium stress, low stress people. The slope through the means, the yellow dashed line, is showing us the between-person effect of x on y. For every unit more person mean stress, average severity goes up by 1. So this slope right here. You can think of this as if you had only measured these people once, and you had 1 dot for them, like this is the cross-sectional slope that you would get. High stress people, medium stress people, low stress people. The individual lines here are illustrating a 0 within person slope. Meaning if I look within the red person here, if I'm higher than my usual level, my severity doesn't change. So it matters in this picture how stressed I tend to be on average. It does not matter how stressed I am relative to my usual. So if these were my conclusions, and I was a researcher who did a longitudinal study, I would be seriously bummed out. Because the whole part of the longitudinal is a null result. Unless people had been saying that it shouldn't have been null, in which null is a finding, and you can still write a paper about that. But you'd have to argue that you have enough power and blah, 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 blah. Speaking of power, which do you think is going to have more power? A level 2 slope or a level 1 slope?
1.
Yeah, level 1, there's more observations. So if you wanted to try and do a sample size planning for a power analysis type thing, you would have to know how many level 1 observations and level 2 observations, but you would also have to be able to anticipate an interclass correlation. To the extent that your predictor values have a strong correlation, then your effective sample size is going to be closer to level 2 than level 1.
Say that one more time.
If you have a predictor that has a very strong interclass correlation, then the level 1 observations, you don't really have as many as you think you do because they have this redundancy. So only if your time-varying predictor had an interclass correlation of 0 is your power for it going to be equal to level 1 sample size. Worst case scenario, if the ICC is 1, your power would be based on level 2 sample size instead, because then it would be completely redundant within the same person. Somewhere between the two is where you'll end up. But generally speaking, the within-person slopes are going to have more power because there's more observations going into making them. Okay, with me so far? All right, here's the opposite. Camera 1, camera 2. Camera 1, camera 2. This is the opposite pattern because now across people of different average stress levels, there is no difference in severity. Between persons, it doesn't matter if you're a high stress or a medium stress or a low stress person, your severity is predicted to be the same. Within persons, though, higher stress than usual is related to greater severity than usual. A 1 unit change in stress corresponds to a 1 unit change in severity. The slope within persons is 1. I don't know why I'm doing my thumb. This is a new one. I don't have a word assigned to the thumb. We're still recording. Okay, just making sure. So now, if this were your longitudinal study, this got a lot more interesting, because you would say that cross-sectionally there's no relationship between these two things. But within persons, there is a relationship. I can think of real-life examples that would go something like this. Hours of sleep and productivity the next day. Do you think it's the case that people who sleep a lot more than other people are more productive? Maybe, but not necessarily. Some people are just wired to not need as much sleep as other people, I think. I wish I were one of those people. I am not. I need at least 8 or 9 hours or I'm useless. But anyone else, who else gets by on less? Anyone need like 6 or 7 to function and you're okay? Yeah? But what happens if you're used to 6 and one night you get 4? Good things or bad things the next day? Nah, probably not as good. The same is true if I take my 9 that I would not like to have and I go down to 7. So in that context, it would be that anyone who gets less sleep than they're used to may have a corresponding decrement in productivity later on, but not necessarily that people who sleep less than other people are less productive people. So there are instances in like that. There's a lot of things in the world where it's like you're used to what you're used to, and to move that needle is deleterious no matter what the used to is. Let's see, these lines are parallel, because right now we're talking about main effects in the models, but you could have an interaction term. I'm not sure if I have a slide about that, but I know that it could be possible. The effect of having the effect of being, let me back up. The effect of more stress than usual could depend on how much stress you're used to. Same thing could be true of sleep. So here is both at once, but of different sizes. So now we have a within person slope that's 1. So each of these lines has a slope of 1. The between person slope is stronger, though it's a slope of 2. That doesn't necessarily mean that it's a bigger effect size, though. It could just mean that the standard deviations of these variables are smaller at level 2, or bigger at level 2, because these are unstandardized coefficients. So this would be for every unit higher stress I have on average, my average severity goes up by 2. For every unit I have more stress than usual, my severity on that occasion goes up by 1. And these effects are in different sizes. So you can have every combination of more or less, different directions, different sizes. Usually in the same direction, but not necessarily. All right. Okay, with me so far? Anything I can clarify, or say again, or say better?
Yes, can you go back to slide 13, the previous one? Because in that case, the between person effect is 0.
Mm-hmm.
However, the level 2 contextual effect would be -1.
Yes, it is.
But we can see that there is no change between groups. What's the interpretation of that?
Okay, you asked for it. The contextual effect is the incremental effect of the person mean after controlling for the absolute value, like the original value of the time-varying predictor. I haven't drawn it in here, but it would be the vertical line, like at 5. So the red people are actually lower stress people. The blue people are the high ones. So for every unit more mean stress you have, your outcome goes down by 1, but only at 5, like after conditioning at the same absolute level of level 1 stress.
Okay.
And this is exactly the problem of between versus contextual, is because what this picture is trying to show is that it doesn't matter how much mean stress you have. But after you introduce this within person effect, it's like the person mean has to take on a negative coefficient to like shut that back down to 0. The contextual effect is the difference. So 0 minus 1 is minus 1. That's where that number came from. And so if you don't know which you have, you might come to the conclusion that differences between people don't matter, that's between, or differences between people actually make it work, like stress is good for you. That's what a negative contextual effect would be, is that the higher stress you have, the lower your severity, and that's not true per se. It's true after you condition on any particular value. Like among people who are at a 5 currently, what is the incremental effect of being a person who tends to have higher versus tends to have lower? The contextual effect makes a lot more sense in cluster data. In cluster data, the analog, if you have people at level 1 and clusters at level 2, a contextual effect says, after I control for the individual value of the predictor, what is the extra effect of being in a group where you have a lot of people that have high values? Like, do you think it helps if you are a student who comes from a privileged economic background? Do you think you have better educational outcomes potentially? Sure. Do you think it matters if you go to a school that has a lot of money? Probably. The contextual effect is like, even if you're a poor kid, the bump you get from going to a rich school is the contextual effect. After controlling for your own SES, what is the incremental effect of the cluster? That makes a lot more sense when you have, after controlling for the individual, what is the extra impact of the group? In this context, it's after controlling for the occasion, what is the extra influence of the person? But level 1 occasions are not unique entities the way that level 1 people are. So to me, controlling for the occasion doesn't, like, I don't want to do that. That doesn't make sense to me. So the other ones, by the way, just to finish this off, if you want to draw these in here, I debated drawing them in here, and I decided I wasn't going to do it. Serves me right. So if you want to show the contextual effect, put a straight line through the 5s. So the slope would be 1 on this slide because it's every unit higher, your severity goes up by 1. The contextual effect would be the 5 on this. The vertical line is the contextual effect here where it's backwards. And then here it would be a 1. The slope of the contextual slope is a 1. It's weird to talk about a vertical line having a slope, but it's a bump, right? It's a jump up, relatively speaking.
The distance between like the points is what you're.
Yes. Hang on. I have, see, where I put the line in was after I went through this whole thing, then I made another slide that has the line in. And I didn't want to like dump everything at you at the same time, so I decided to hold back the contextual effect, but yeah, it's this line. So I have a paper that I wrote with Rob Stosky when I was a postdoc. I think it was published like 2006 or 7. And it's the of the papers that I wrote, like as first author, it's the most highly cited one. And I made a picture like this, and in the picture I had drawn this line, and in the publication they left it out. And I was so frustrated. I was like, but this line is my contribution, okay? Like, and so I had to like go and like edit the PDF and like stick the line back in. Like, no, that way when I put the article up, it has the line corrected. So I was so frustrated when they left out this one line. But this is the contextual effect. Yes.
And so, like, from visually, what it means is, like, the further to the right your line is, like, the green is further than the right, or further than the red, and the blue is further than the green. That is what drives it up further, like, north on the graph.
Yeah, so the extent to which the within and between slopes are the same. Like if you picture these lines sort of collapsing in on themselves, like if the green sort of picked up where the red left off and like if they all aligned such that there was no vertical distance between them, then that would be a situation where the within and between effects would be the same. Like they're all on the same, remember the age convergence plots where everyone's on the same thing? Like picture that. I need to make that slide. I'll make that slide, and I'll stick it in here, and we can talk about it next time. But that's what I'm picturing. So the extent to which they diverge is the contextual effect. The between effect is the slope of this yellow line right here through the means. And the within is the slope of the individual lines. But this is like, yeah, slide a million, so we're going to go back to these for now. I don't think contextual effects are useful in this context. I just don't. I think they're confusing. And I would just love to skip that entire whole thing with you and not even tell you about them. But I have to, because by default you're going to get contextual effects out of M+, whether you like it or not. And so I'll need to teach you how to turn them into between effects, so that we don't confuse people as to whether being a person who's high in stress matters or not. It does, yes.
So in this case, if those three lines would have the same between and within effect for that variable, those three different lines would be almost the same line.
That's right.
Okay.
I have a picture. Let me see if I can pull it up in the I'm angry at M+ paper. Here it is. I know I made those pictures. Let me see if I can find them real quick. So yes, this is one of the things I'd like you to read. I don't mention my readings very much, but let's see, this one. This is another one. I thought I put one where they were all pushed on top of each other too, to sort of illustrate like what would happen. I have a memory of this. Maybe it's a false memory. There! It's not a false memory. I did this. Isn't it amazing how you can work like really hard and long at something and then like it's gone? You know, like, oh yeah, I have a vague memory of doing this, and I'm glad that vague memory isn't just a fake memory. But this is what it would look like if there is basically no contextual effect. So I made this sort of generic in terms of level 1 and level 2 because I didn't want to talk about longitudinal or clustered, but this would be like a low person, medium person, high person, and they all kind of line up on the same trajectory. So I introduced a contextual effect that was 0.2, just so the lines wouldn't be straight on top of each other, but this distance right here shows that after you control for how much level 1 whatever you have right now, what you have the rest of the time doesn't matter. In contrast, something like this, which is the between effect is 0, the within effect is 1, and the contextual effect is -1. So this is what I drew in the PowerPoints. Then it's after you control for the fact that you're at 0, what does the incremental contribution of the person mean? And it's actually backwards. So the squares, let me read this, are low people. So like if you are relatively high for yourself, like this square right here is from a low person who's on a high day, like they have a different outcome than a high person on a low day. And the words I use for this are similarly bad. I remember like struggling to try and explain this. But the problem is that like the -1 here versus the 0. Does being a high X person matter? Or is it bad for you? Like those are two different conclusions based on whether how you're thinking about controlling for the level 1 part. There, that's the slide I should have made. I did make it, I just didn't put it in your slide deck. Okay, 119. How are we doing?
It is the week before spring break.
It is, but we're all here. I think everyone's awake. Right, Zoomers? We're awake? Can't tell immediately. Oh, yes. Everyone's like, I'm awake. Good. I'm awake too, for now. Let's see. I got a story. So those of you who came to my workshop last summer, do you remember that? A few of you did. I gave was it 4 days? I think it was. Yeah, it's all gone from my memory now. But I stood here and I talked for 4 days, and this was in that slide deck. So you may have seen it before, but but I'm going to assume that you haven't seen it before, or it's been at least a year and you don't remember what it was. This is the end result of a story that I started last semester. This was example 4 out of the longitudinal class looking at alternative covariant structure models, where we went through like autoregressive and compound symmetry and the Toeplitz and the heterogeneous versions and this whole thing. These are real data from a friend of mine's dissertation. She was looking at the relationship between stress and psoriasis severity, which is a severity outcome that is thought to be exacerbated by stress. And these are the trajectories of her sample. So she was able to get just patients from a clinic that were already undergoing treatment. This wasn't an intervention of any kind, and she just sent them questionnaires in the mail, like, hey, can you tell me how bad your psoriasis is this week, and answer these other questionnaires? And she was the person who went into her dissertation proposal with a nice cross-sectional design where she was going to measure like forgiveness and coping and stress and psoriasis and look at moderation and coping stuff. And she came out of her dissertation proposal with her committee having added on a longitudinal component to her dissertation over an 8-week period in the summertime. So we ended up, the model that fit best with respect to severity was a random intercept with like a lag 3 correlation and maybe heterogeneous variances. So it was a fairly complex structure to describe this, even though there's no change over time per se. So what she wanted to know, though, then is how is stress related to psoriasis? So then the first part of this, step 1, empty means models, always. Figure out if you actually have longitudinal variation in the first place, otherwise game over. So for each outcome, we fit a model that looked like this, compute our interclass correlation. For severity, the interclass correlation was 0.83, and for stress, it was 0.56. So what do I make of these numbers?
3% of the variance in the severity outcome is attributable to between persons.
83% of severity is between persons. Some people have a worse condition than others on average. Or the way that I described it last semester, this is an 83% waste of her time. It is. This is what she already had from her cross-sectional study. Some people have worse disease progression or severity than others. So she got 17% of new information here to start with. Stress, though, is more balanced. But because stress has an interclass correlation below 1, we know that it is time varying. Because its interclass correlation is above 0, we know that it has some level 2 component to it as well. So it's 2 variables in 1. This was the R correlation matrix we ended up with after fitting the Toeplitz lag structure. So after controlling for the 83%, essentially after putting the random intercept variance in G, then weeks that were adjacent were correlated about 0.5. 2-week lag was correlated about 0.36, 3 weeks was 0.1, and after that it didn't matter. So how severe you are last week is related to how severe you are this week. There's like a carryover kind of situation. So here's what the model looked like. And this was a model that I was able to help her with her data after she graduated, by the way. We didn't know what to do with the data at the time. And it wasn't my job to figure it out because it wasn't my dissertation. But afterwards, we wanted to do something with this, and I remember when I was a postdoc, we had this thing called Methods Lunch at Penn State, where it was literally like all the methodologists from the HDFS department, psychology didn't really play with us for whatever reason, but there were some other ones too. We all sat around the table, and people would come and like ask for statistical consulting help, and we'd eat and argue with each other, and the students would sort of sit in the background afraid to talk. And that was like me at first, and then eventually I was like, I have an idea. And then over the course of 2 years, every time I raised my hand, they'd start laughing. It's like, okay, she's going to turn this into a multi-level model, watch. And I'd be like, are these students nested in classrooms? Yes. Boom. Like, is this data longitudinal? Yes. Boom. Right. Do you have multiple siblings from the same family? Because that was a very common design in human development and family studies, to study families with multiple people. Boom. So yes, I could turn any design into a multi-level model at the drop of a hat, but that's because everything is a multi-level. It's not my fault. okay? But I didn't know like how to think about this problem because this wasn't a growth curve. And the way that I had learned multi-level models is you do growth curve analyses. And I'm like, but there's no, like, time doesn't have an effect here. I don't know what to do with these data. So I presented the slides, like the pictures and the whole thing, and then the person was like, just leave time out. Just fit a multi-level model and leave time out. You can do that? Yeah, it's called a fluctuation study. So I eventually did figure out what to do with it, and that was to carve up stress into two different types of variables. So I have person mean stress, which I had centered at 2 because that was near the grand mean. And I have 2 different slopes in at level 1 because one of the hypotheses that she wanted to address was whether it took time for whatever mechanism is relating stress and severity to play out. Like, you don't just automatically have like a skin problem the second that you're feeling more stress. It takes time to show up. So we have the lag 0, which is time varying stress minus the original person mean. And then we have the lag 1, where I took the data set and shifted everything down a row so that the predictor from last week was on the same line as the outcome from this week. So when you're doing lagged analyses with observed variables, you literally have to shove the data down to be able to get everything onto the same row to do this. So it's the idea of between and within, but there's 2 different kinds of within, this week's stress and last week's stress. So if I look at the fixed effects from this model, the intercept is not at time 0 like it normally would be because we don't have time 0. It's when person mean stress is at 2 on a week where you have as much stress as you usually tend to have. So when these within person variables are 0 is when you're at your own mean. Does that make sense? When you're at your own mean is when the within person variable is 0 because this is how it's computed. It doesn't matter if it's week 1 or week 2 or week 3. Although, because I'm interested in a lagged effect, I can't include week 1. So I had to throw away the first occasion because I don't have a prior stress variable to put into week 1. So this is weeks 2 through 8. If I were interested in a 2-week lag, could I do that? Sure, if I'm willing to throw away weeks 1 and 2, because I don't have the lag variable to fit into those. So that's the downside of this univariate framework in lagged effects. So intercept would be expected psoriasis severity for basically an average person who was at their average this week and last week. The between person slope, gamma O1, is going to be the difference in severity for every unit person mean stress. And the within person slopes, gamma 1, or 1O and 2O, are the change in severity that week for every unit higher stress than usual this week and last week. So relatively more stress than usual is going to affect your outcome at that same occasion. That's the idea. And I have a note here, these 2 slopes are fixed only. I don't have a random slope in the model yet. Turns out I didn't need one, but this is complicated enough. So here's what ended up happening. The fixed intercept severity score was about 2. This is on a weird logged outcome that I don't even know what the values are, but higher it means worse severity. I have a significant between person effect. So for every unit higher person mean stress, overall severity on average across the study goes up by 0.5. So this was the cross-sectional relationship that she was anticipating in the first place. People who have higher stress than other people have a higher rated severity of their psoriasis. This is all self-report, by the way. The lag 0 coefficient was not significant, but the lag 1 was. So for every unit more stress you had last week than usual, this week's severity goes up by 0.06, which is a tiny number, but it was significant given the sample. There's no effect that was different than 0 for having more stress than usual this week on this week's outcome. So the terminology for this sort of lagged effects in general, if it's the same variable predicting itself over time, that tends to be called an autoregressive effect instead. If it's cross variables, like this week's X predicting next week's Y or vice versa, those tend to be called cross lag, like cross variable analysis. Not to be confused with cross level, which is a different word, meaning a different thing. So lagged effect is a general term. These are more specific flavors. So she does have one little reason to have done the longitudinal study, one little p-value. It's a marginal p-value though, and the other part of the example that I don't have in here is that this p-value becomes non-significant if you fit the wrong ACS model to severity. If you fit an autoregressive model instead or something, it becomes non-significant. Because as you all wrote in your homework 1, the standard errors for the fixed effects that you care about are a function of your model for the variance. You get the model for the variance wrong, you get the standard errors wrong. These are real data, so I don't know what the right standard error is, but I can do model comparisons to decide what the right model for the variance is and go from there. Okay, here's some syntax, because it was in my workshop, of how we would do this model in SAS, Elmer, Stata, and SPSS. Okay, 131. How are we doing? Yes,
Lisa, can you explain again in slide 17,
I can try.
please? Because the interpretation of gamma 0, 0, the intercept, I can understand that it is fixed at the person mean stress equal to, because that's the constant we use to center the level 2 variable.
Correct.
But then you said, and who had severity equal to last week and currently.
Yes,
Where is that 2 coming from?
because let's say that our reference person, we're talking about the effect for somebody who has a person mean stress of 2. So like they'd be at 0. So a 0 score on the within person variables would only be obtained if you currently have a 2 minus your mean of 2. So the within person X is how much more than your mean do you have? And so when within person X is 0, it means you're at your mean.
Oh, okay.
And the mean has a reference of 2, so therefore you're at your mean, which is at your 2.
Great.
Yep.
Thank you.
Yeah, and it's this, then the difference is just this week's column or last week's column. All right, let's see, 132, I gotta decide which way I wanna go with this. And do I wanna do contextual or not? I don't wanna do that yet. You wanna look at another example for a few minutes? Yeah, nodding. I don't wanna do contextual yet. I don't have the strength. We'll start example 4A. We won't get very far though, because I can read the room. But even though it is the week before spring break, I am contractually obligated to keep talking. You understand that, right? Like Jonathan and I joke about how like the students will never be sad, right, if we end class early or cut out a homework or do other things, but then like we feel bad, like we're somehow letting y'all down. So, but I can read the room, and I promise this won't go far. This is another based on a true story. So as you can see, I'm like 1, 2, 3, 4, 6th author on this publication, for which I did all of the analyses and wrote all of the results section. So you can do the math on that. This was from when I was a postdoc. So these are folks that I collaborated with on the University of San Francisco's Medical Center, I want to say, something like that. They paid me money, so it's not all for bad. You know, I maintain my my belief that if you learn how to do this stuff, someone will always pay you so that they don't have to. That's how it works. But this is simulated data based on the real data that were in these paper. They were looking at type 2 diabetics and wanting to look at within-person processes as opposed to cross-sectional relationships to see to what extent things like stress and mood and social support were affecting morning glucose, which is an indication as to how well controlled their diabetes is. So we don't want glucose that's too high, but we also don't want it to fluctuate too much. So differences in fluctuation could have been part of the story, but I didn't have that as part of this analysis. So we're looking at negative mood as a predictor of glucose. and we're looking at gender differences in the affective negative mood. So just 2 variables in the story today. In the original data, I did all kinds of analyses looking at alternative covariant structure stuff for the glucose outcome, and it only needed a random intercept. That was like, everything else was like, nope, don't need it, don't need it. Okay, so we'll go simple on that. I know, what a world. It's like, all right, okay, I'll do it easily. So we have, let's see here, the data manipulation steps here, and I've got 2 different versions of the variables because we're going to do person mean centering as God intended first, and then go to grand mean centering and contextual effects after that. So my God, at least, you know, the one that I pray to, likes between and within. Okay, so these are fake data, which means you have them in your download folder, by the way. So I have person mean negative mood as the first thing I need to do is make that variable so that I can carve these things up. So I looked up how to do it in Stata and was pleasantly surprised to see that this is 1 line of code. I tried to find how to do this in R. It was not 1 line of code. It was many lines of code and potential tidyverse versions of the lines of code. So then I went through, I was like, nope, I'm going to get Jonathan on this. And it turns out in the clustered class, he made a function in R called add unit means. And then it's 1 line of code. So I stole his function and put it in my handout, but I'm giving him credit for that. Because this is a very nice feature. It's not one line of code in SAS either. But egen in Stata is like fancy gen, like if you want to make a new variable that's some kind of more complicated. So mean of negative mood by ID is taking, basically aggregating across the rows of the same person, coming up with a mean across those rows, and concatenating that to the data set where the mean is all the way down all the rows for a person. So we need the mean to be in every row for it to go into the analysis. And it's doing all of those things in 1 step. I am centering negative mood at 0. So if you're looking at that and going, why? It's to remind you that you need to do this. The negative mood variable that we worked with in this study was actually a z-score of a latent trait where the mean was 0. Like it was in a z-score metric, I should say. It was a latent variable that had a mean of 0 and a standard deviation of 1. And so the mean was near 0 in this data set. So I am going through this process purely as a pedagogical exercise to remind you that if you have a person mean of a predictor, you should pick a constant to center it with if 0 is not within the scale. If 0 is within the scale, go ahead. So I have PMNM0, which to me means person mean negative mood centered at 0. That's my level 2 variable. That level 2 variable is only level 2 variability. It is a time invariant predictor. It is the level 2 part of time varying negative mood. This variable is going to be in all the models because the distinction about grand mean centering versus person mean centering happens at level 1. So to stick with person mean centering, I'm making a variable called WPNM, which to me stands for within person negative mood, which is the original negative mood column minus the original person mean negative mood. So when within person negative mood is 0, that means I'm at my own mean. When it's a positive number, it means I am grumpier than usual. When it's a negative number, I am less grumpy than usual. And yes, we use those words in the paper. Grumpier than usual is better than a 1 unit increase in the indicator of negative mood. And then we had a binary gender variable in which men are the reference and women are the alternative group. R code. Here's Jonathan's function. So thank you to that. It's inside the R download folder. He made a function called add unit means in which you say, where do you want the function to return the result? And I'm sticking it in the same data set. So it's taking the data set and adding a column. How do you want to organize your rows? Like what variable tells you which rows go with the same person? That's level 2 ID. What variables do you want to take the mean of? Negative mood is the original time varying column. And then what do you want to call them is this. So in his example, he had done like 3 in a row. So inside, so I left this so that you could like add them. you know, like that way. The C thing, concatenate, is that what that stands for? Combine? Yeah. I don't know. I just know that if you need more than one thing, you need a C function. That's what I've learned.
I think it stands for contain, like a container.
A container. Well, that's yet a third C that would work in this situation. So, yeah. So I borrowed his function to do this. Then otherwise, I created the same variables, person mean, negative mood, centered at 0 for pedagogical purposes, the within person version, and the time varying version will be forthcoming, but not today. So that's the setup for the model. Do we have the strength for an empty model?
Yes.
Okay, good. Because if not, then that means we need some help. So step 1, figure out how much variance is between and within in each outcome. So I have log glucose the next morning. So the data set is set up so the next morning's glucose is on the same line as all of my predictors. So it's like whatever happened yesterday will show up in your blood work the next morning is the idea. I'm in REML for this example because I can be, because this is a univariate approach. Everything is as you're used to seeing it. So this is for glucose. I have only R output since Stata users are well acquainted with Stata mixed by this point. In Elmer, I have to ask for -2 log likelihood to be given separately, so I added that call before the summary so that the -2 log likelihood would be the first thing you check. Here's my variance components for my outcome, and here's my interclass correlation of 0.69. And then I did a RANOVA call to see if that interclass correlation is significant. So it's comparing a model that doesn't have a random intercept to a model that does. And the likelihood ratio test statistic is 4,000. So yeah, we'll call that significant. So is this variable more between or more within?
More between.
More between. So there are differences between people that are relatively more salient in how well controlled their glucose is. So that means that any predictor we ideally would match. Like to be most effective, you would want the distributions to be relatively the same. Nathan says C stands for combine. I think that was I said concatenate first, but combine works for that too. So I don't know, chunk it together. Negative mood as a predictor. So even though I'm thinking of this conceptually as a predictor, I'm treating it as an outcome. Because it's my concept, right? Someone else might have a research question about what predicts negative mood. That's a perfectly reasonable thing to do. Why do my little things move around? I don't know. Some of my boxes move without my permission sometimes. This one has an interclass correlation of 0.39. So is it more between or more within?
More within.
Yeah. Only 39% between. So they're a little bit asymmetric, but not horrible. And this is also significant. So we know then that negative mood is contains grumpy people and less grumpy people, and it contains grumpy days and less grumpy days as two different things. And we're going to put those two different things in the model on Thursday. But not today. All right, questions?
I have a question, but it's not about this, it's about latent basis stuff.
Okay, then I will answer your question after I say goodbye to everybody, unless they
Okay.
want to hear about latent basis stuff. That way, if folks need to go, they can. All right, thanks for being here. I will see you on Thursday, I hope. Hang in there, folks. We are getting there. Okay, ask me your question, please.
So, for latent basis stuff, do we have to fix if we're doing it like SEM, multivariate SEM style, do you fix the mean and variance to 0 and 1 for the random intercept factor?
It depends on whether this is a higher order growth model or just a regular growth model on the boxes. What's your context?
Higher order.
Higher order. Then the variance of the random intercept factor is always estimated because the loadings are fixed to 1 instead. But the mean of the random intercept factor would probably be fixed to 0 if you estimated all the lowest order intercepts instead.
That's why Stan is blowing up. Okay.
Yeah, it's
Because I was
not
trying to fix
identified.
it to 1, and it did not like that at all.
Yeah, it shouldn't
Um,
like that.
And then is the mean, so the mean of this, I'm just gonna call them circles, okay?
Sure.
The mean of the circles for random intercepts and slopes is the average variance over the 3 occasions?
It's
or over
the mean
number
of the circle
occasions?
is always a fixed effect.
Okay,
So the mean of the random intercept circle is the fixed intercept. The mean of any slope circle is the fixed slope that goes with that basis function.
so would the 0 star 1 would be the
Uh,
means? Or
what
the
program?
loadings?
What program are you in?
I understand, so that's not gonna
Okay,
help.
yeah, so
Um,
star in M plus means free, and star in Levon means fixed. I don't know what star means in Stan.
Well, you would estimate, that would just be a parameter to estimate, so.
Okay,
But you're saying that the mean of the random slope circle
yes,
is the fixed slope
yes.
for, okay. So if I told you that my random slope mean was -1.3,
People are going down on average by 1.3 if the one of the latent bases is at the end, and then that's the total amount of change on average.
okay. So in the latent basis, the loading that's starred is the mean that you're estimating.
It's not a mean, it's just a parameter, it's just a loading, it's a
Okay.
slope.
Okay, I think I understand. So, but at the end of the day, we fix the mean of the random intercept to 0, we estimate its variance, and then we can estimate the mean and variance of the random slope factor.
Yes, all of that works, assuming that you've estimated the intercepts at the lowest level, then the random intercepts mean for the fixed intercept has to be 0.
And since I'm doing ordinal regression, would there be a residual term?
Depends on your estimator. If you're in maximum likelihood type stuff, then there's no residual variance. If you're in
Because
some
it's
kind
constant.
of, yeah, it's 3.29 if you're in
Okay.
logits. Otherwise, if you're in diagonally weighted least squares, like some kind of limited information polychoric land, then yeah, you could conceivably have them after you after you add the invariance constraints.
Okay, because when you're in the weighted least squares multivariate, you're treating it as like a normally distributed, conditionally normally distributed model, which would have a residual term.
No, it's just that you're maximizing, you're trying to find the parameters that best recreate the polychoric correlation matrix.
Okay,
And residual variances become identified after you have invariance constraints because they're basically like the slop factor that the invariance doesn't, to the extent that it doesn't hold, that has to go somewhere and it goes into residual variance.
okay. So I think I understand now. I think it was, so maybe I'll come to Oxnard tomorrow, because the mean, I'm still a little confused about like the mean of the random effects factors for like the slope.
Yeah, so there's a good reason for confusion is because there's not necessarily one right answer. It depends on what the rest of the model looks like.
Okay,
So
so maybe
I have to
I'll come, tentatively, I'll come tomorrow and maybe just bring the picture that I have, and because Stan, I mean, it's really not that off, like, it's not that much different, if you can believe it, but you just have to, the coding is in C++, so it looks wonky.
Okay, well, if you can tell me what you're trying to do, then I can tell you whether that makes sense.
Okay, that sounds good. Thank you, Lisa.
You're welcome. By the way, do you want this conversation on YouTube, or do you want me to cut the video before it starts?
If people love Stan, maybe this is me advocating for Stan, raising awareness for the love
Oh my
of Stan.
goodness, you and Jonathan. He loves Stan too, and I don't get it, but whatever. Okay, I'll leave it on there to raise awareness that you're a Stan fan.
And it might help me, because I might come back to this later, because
Okay,
I'm working on this tonight, but anyway, thank
Yeah.
you again.
no problem. All right, catch you later.